Good afternoon and welcome to the Van Andel Institute. We're in for a real treat today. We want to welcome to our public lecture series. Today's title called A Focus on Translational Medicine. My name is Brett Holloman. I'm the Chief Development Officer here at the Institute, and we're pleased to have you join us. Thank you for taking the time out of your schedules. Today, we have the opportunity to hear from two extraordinary physician scientists who have a deep understanding of how both great science and the discoveries that take place in the laboratory can be translated into life-changing therapies for cancer and other human diseases in the clinic. We're fortunate to have such incredible scientific talent located right here in Grand Rapids, Michigan, and within the Institute. It's my pleasure to welcome our two experts who have deep knowledge that straddles both the clinical as well as the biomedical research space as well. Dr. Stephen Balin is the co-leader of the Van Andel Institute Stand Up to Cancer Epigenetics Dream Team, a director's scholar at Van Andel Institute, and co-head of cancer biology at the Sidney Kimmel Comprehensive Cancer Center at Johns Hopkins University in Baltimore, Maryland. And don't say that 10 times or you'll tie your tongue. Dr. Balin studies the body's genetic control systems called epigenetics, which is searching for vulnerabilities in cancer. Dr. Balin is a true pioneer in this field and was among the first to trace epigenetic causes of cancer. His studies have led to new therapies for breast, lung, and colorectal cancers, amongst others. We're also privileged today to be joined by Dr. Matt Steensma. Dr. Steensma joined Van Andel Institute in 2010 as an associate scientific investigator in the Center for Skeletal Disease Research. In 2014, Dr. Steensma was named one of the winners of the inaugural Francis S. Collins Scholars Program in Neurofibromatosis Clinical and Translational Research. Dr. Steensma studies the genetic and molecular factors that cause benign tumors to become cancers and to find vulnerabilities that may be targeted for treatment. As a scientist at Van Andel Institute and a practicing surgeon at Spectrum Health Helen DeVos Children's Hospital, Dr. Steensma is committed to translating scientific discoveries into treatments that improve patients' lives today. In addition to being phenomenal physician scientists, both Dr. Balin and Dr. Steensma are remarkable human beings with an incredible compassionate heart and deep committed care for their patients. It's my privilege today to introduce Drs. Balin and Steensma. And before we hear from them, as a start to our program and as a foundational underpinnings to the work that they're going to share, we have a video that we'll share to introduce both Dr. Balin, and then after Dr. Balin speaks, we'll have a video that introduces some of the work that Dr. Steensma is doing as well. So let's begin today's program by enjoying the brief video.
At the Van Andel Research Institute, we expand our footprint way beyond Grand Rapids. By collaborating with the best institutions in the world, we can act as a hub to bring academic institutions and disparate drug companies, which might be essentially competing with each other, to actually collaborate with each other so that we can actually impact human health in this way.
We were introduced to a fascinating paradigm, the mission of Stand Up to Cancer. And that is to marry basic endeavors in the laboratory in a way that's almost seamless with some of the possibilities that we can translate those findings to the bedside. Bench science to the bedside, work to improve the management of cancer, total mission of Stand Up to Cancer.
Although the Van Andel Research Institute doesn't treat patients, the contribution that they make in terms of facilitating getting clinical trials done is extraordinarily important.
So the importance of a clinical trial is simply that it gives so many people hope for what's next. Over the years, I remember chemo being where once you're done with chemo, that's it. You know, there's nothing else that we can do for you. it takes those words out of the doctor's vocabulary so soon, because you may be on a clinical trial, but while you're on that clinical trial, your doctor is rallying for you because they're looking at the dynamic of what your cancer is doing while you're on that clinical trial from blood work. And they're also preparing for what's next based on the next clinical trial that may come available. It may be the difference between life and death.
All of us at Stand Up to Cancer are so proud to collaborate with the Van Andel Research Institute. I think epigenetics is one of the most exciting areas of cancer research today, and we're profoundly grateful that the Van Andel Research Institute stood up, if you will, making such a significant financial and organizational commitment to grow the work of the original Epigenetics Dream Team. If you could look up extraordinary scientific collaboration in the dictionary, there would be a photo of Dr. Jones and Balin together. They and their team are the personification of what Stand Up to Cancer is all about. So thank you for helping us do so much to help patients.
Please join me in welcoming Dr. Stephen Balin.
Well, thank you so much. It's an honor to be given the chance to speak to you, and I want to thank you for showing up to hear what we have to say. I quite frankly, I'm not sure I could say it any better than what you just heard, or any better than that patient, Trina, just told you. I'm going to try to tell you about the process that Trina engaged in a clinical trial, which gave her some years of life with colon cancer that she might not otherwise have had. Not long enough, but years to do things she never dreamed she would do. She became a model. She took care of her son in a way that he won't forget. So let me tell you and try to explain to you the process that she engaged in the stand-up of cancer that you just heard about. So, translational research at the Van Andel Institute. How does a basic research institute, which is not a hospital, as Dr. Jones just told you, take the knowledge being generated in that institute and take it to the benefit of patients with diseases like cancer, and do this all over the country, and indeed spread the concepts all over the world? How do they do that? So first, let's talk about what is translational research, because it's a confusing term even to the people who are in it sometimes and define it. But what it really means in a simple way is that you take basic fundamental findings, decide which ones can go forward to benefit patients, and translate it to the patients by doing something like a clinical trial. And I'll show you, turn the arrows around, because sometimes it goes in the opposite direction. It goes from the patient back to the laboratory to understand, and even back to the clinic after that. Fundamentally, that's translational research. And if we get specific about what we try to do within the framework of the Stand Up to Cancer, is to take the best laboratory science, make wise decisions about what we can do by taking that science to understand, how does cancer start, how does it go forward, and how do we milk that knowledge to take it to the bedside? The ultimate goal is indeed, first, decide what's ready. And that is a big decision that scientists who do translational research have to make, because if they do it wrong there, then all may be doomed to failure. So they make that decision, they take it to patients. Now, what's the dream? We're a dream team. Well, the dream is that what we're doing when we do this is benefit patients in such a way that we may actually change the management of cancer, even the most common and the most deadly ones, in a good way for patients. In the end, where we can, pursue a cure. Difficult to come by, but we're certainly always looking for that. And maybe even a more realistic goal, which is terribly important and could apply to Trina, who you just saw. Try to make cancer a more chronic disease, say like diabetes, which can be managed in a long-term way for patients such that they not only survive, but they do it with a high quality of life. And this is a very important mission and goal of this team. So when we engage in clinical trials, just to explain trials to you very briefly, they go through phases of graduation. When you start with a concept, maybe it's new drugs or something we start, one of the first things we have to do in a phase 1 called a stage of this is decide whether it's safe. That's very important. We usually now marry that in a trial that's called a phase 1 and 2, because if we decide this and how we can do it, we're immediately beginning to look to some degree of effectiveness. Generally, when we bring in new trials, it's going to be in a rather small trial, 100, maybe 50 people, but we're looking for that sign of effectiveness in this trial that we can take forward ourselves, or more often, if it's bigger, it may be taken in a way by others forward from the concept we derived, and take it to a bigger trial that could go up to thousands of patients, to 100. And if that is successful, take it all the way to the ultimate, where the FDA in this country approves that concept and the drugs, where they now are in the doctor's office after that, and the patients have access to them and can get them through their insurance and other mechanisms. Lofty goals, very difficult to accomplish, but it's our hope and what we dream. So how do we do this? What is the Stand Up to Cancer? So the Stand Up to Cancer was a concept started by 9 women in Hollywood, one of whom you just saw, Katie Couric, producers of movies, all in the entertainment business, who decided if scientists would work more together and pool their knowledge and not compete, we could move faster to do something about cancer. Now, coming out of Hollywood, if you left it there, that might be a concept. You say, how in the world is that going to work? But they were very smart, because they paired with the American Association for Cancer Research, our leading research called the AACR for short, who took over peer review and decided which teams actually could be constituted. And they hold our feet to the fire, even though we're Van Andel Stand Up to Cancer now. All too regularly, they hold their feet to the fire. They look at what we're doing, and they tell us when they think it's not too good or whether it's right. So it's a very organized and really rigorous process. Now, how does the Van Andel Institute do what Dr. Jones just said to you? This basic institute, this is one of the most unique arrangements, and you should be very proud of this in Grand Rapids, that I think you will see. Because the Van Andel Research Institute, with the SU2C, and other diseases as well, actually selectively helps funds around this wheel to take this research to partners on the outside. They take the basic research, and through philanthropic support, they do this in Parkinson's disease, the cure for Parkinson's, the Michael Fox Foundation, Stand Up to Cancer that we're talking about, bring all this to clinical trials. And I'll mention the right side here in a moment. And they do this by partnering and helping to sponsor at the best cancer centers in this country to conduct the clinical trials. Memorial Sloan Kettering in New York, Johns Hopkins, Michigan State, even in Australia, the Garvan Institute. We have a branch, a team working in Denmark now, Indiana University. So it's a wheel of participation spreading out from this core from the Van Andel Institute. And it's even beginning to start forming participations of local hospitals here who are forming the ability to do some of these trials, such as at Spectrum Health. And this gives us the power to bring our fundamental ideas to the major drug companies in the country and say, will you help us? Will you contribute to the support of the trial? Or can we get the drugs from you that we need? Very expensive and not easy things to craft. But the power of this team is often very successful in getting the drug partners from the companies to help us do these trials. Now I'm going to get a little complex and deconstruct it for you. What is epigenetics? We have to come and try to understand this a little bit. So I like to think of it this way. You all have heard of DNA, you know the double, you see it as this helix. And the DNA has every ability to do anything a normal or an abnormal cell in your body might do. But the DNA alone is a hard drive. And unless it works, or it's like a piece of music on a sheet without an orchestra to play it. So how do we make it function? It needs a software, and indeed, that's all, it needs a package. If I were to take the DNA in a tiny little cell that you can see only under the microscope, pick up this DNA linear like that, and throw it as best my arm would do it across this auditorium, it would go out the back of the auditorium, out the front, into the streets, and head down into Grand Rapids. How do you get that DNA packaged into this tiny cell when it's like that? And so you do it by packaging, wrapping up in these little balls, which you call nucleosomes. It's not important what the term is, but you wrap your DNA around this, and then you move the nucleosomes around. So if you have an area like this, which is packed with these nucleosomes, if there's a gene under there, it probably is not one the cell wants to use because it's got it packaged away like this. If it's in this more open configuration of nucleosomes, then that's generally the territory that gene you're using, either constantly or you need to call on, will function. Now, that's what happens if it goes right, and I'll show you the consequences of that. But cancer, just like the hard drive, can go wrong. You can have mutations in the hard drive that help drive the cancer. Your epigenome or your epigenetics can go awry as well. So you can have a gene sitting here like this that shouldn't be like that, shouldn't be all wrapped up. You need it. Maybe it's a gene you need to help stop a cancer. The hard drive's fine. The gene's under there, it's okay, but it's wrapped up in the wrong way. And what we do is to take drugs that target the various proteins that actually orchestrate this. A protein that puts on a mark called DNA methylation, a drug that Peter Jones actually showed its action, can remove that DNA methylation and help unpack this and change it to a more favorable territory for that gene to come on, or in the opposite direction if the gene is abnormally in an expression pattern like this. The key thing about this is it's very hard to reverse an abnormality in the hard drive of DNA, a mutation. But this is, I'm just telling you, is a reversible process. In the laboratory and now even in patients, you can use the drugs to make that switch. And that's the key. And the drug azacitidine that Peter Jones discovered the mechanism is now approved by the FDA for use in certain pre-leukemic and leukemic disorders, which we study. But one of our main missions is, can we do this in the deadliest cancers, the so-called solid cancers? Can we do this in lung cancer? 160,000 cases of lung cancer a year in this country, 160,000 people a year die. Multiply that around the world, that's 1 million people who die of that disease alone. Can we do something about that using what we call epigenetic therapy? I want to show you what it looks like when everything goes right. The hard drive under that blue spot in the founder is exactly the same as the hard drive under the white spot. It's not any different. Same for this zebra. The hard drive in the black stripe is the same as the hard drive in the white stripe. This is a mouse that has one epigenetic disorder in it, such that when it eats, it gets too fat, and when it eats, it actually changes from its normal brown color to a golden color. And look at these two twins. They have identical hard drives. They couldn't be any more identical. And yet, if you watch their genes function over time, they start to show difference in the function of the genes and which ones are working in different ways. They may become, over time, if they live apart, prone to different diseases. And generally, that's not, they share the hard drive. They don't share the way the packaging plays out over time. And so this gives you how that works. But what about cancer? So studies in our team and other workers around the world have really found that things that damage the hard drive also damage the packaging. And those things are inherent to why we have risks for cancer. The leading cause of cancer is chronic inflammation that just keeps on occurring and occurring. And unfortunately, aging is somewhat like that. So one of the leading risks for cancer is for most cancers as we get older and we age. We've learned that environmental stress and even emotional stress, all of these things can create an abnormal packaging of the type that I just described to you. And this has major ramifications and hopes for the future. So it's shown here, irritants, cold air for people who are sensitive to it when they're running, smoking, certain medications which may help but also are exposing can cause these abnormalities. And this has a fundamental consequence about how manipulating this plays out, because when we talk about that translational science and the ultimate goal and the dream, this has, for the future, ways that we can use epigenetics for prevention, simple things that you do, the right diet, stop smoking, and exercise can be healthy for your epigenome. and help delay the kinds of changes that it may serve for cancer. If we're at risk for a cancer from a benign lesion like a colon polyp, then we could probably intervene in people at high risk for that and maybe switch that around and cut the time down where that progression would help. And I'm going to talk about the treatment of established disease, but I want to remind you there are other ramifications we can start to think about that epigenetics and its manipulation could be fundamental to in your lifestyle and all of this. So pictures are worth 1,000 words. Trina was. So let me tell you about what this picture is. When we started back in our clinical trials, we did indeed use a low dose of that drug, Fidesa, married to another drug that helps that drug work, and went after patients with advanced non-small cell lung cancer. That's the biggest killer we have. And when that disease is advanced, even with current treatments, the life expectancy, 5% survival at 5 years. So this is something that we want to change. So this is one of only 2 patients out of 65 that did what I'm going to show you. But imagine we're trying to work if we could tell who those 2 patients were. Because for the statistics that I just told you, think of the hundreds of thousands of people across the world that would be if you knew who to do this for. Because what happened here, these 2 patients had a tremendous response to our epigenetic therapy alone. So this is a wonderful gentleman that I got to listen to in an interview and just sit and listen to him. He was a fireman in his 60s from Baltimore. And he came in very sick. He had this big lesion, this mass here, this white mark should not be there in his otherwise black lungs. His airways as they enter the lung should not be enmeshed in this bulky mass here, and this hole that you see on the scan in his liver is a metastasis. And he was very sick, and he poignantly said at that point, one of my big regrets, he said, is that I'm not going to live long enough to fulfill a promise I make to my grandchildren. I'm going to build them a sandbox. And he went on his trial. And so here he is about 2 months into the trial. Maybe we're getting some shrinkage. Look at the holes getting smaller. 6 months in, the hole's gone. Most of this is cleared up. And 8 months, and he lived 4 years. And he built the sandbox, and he did a lot of other things that he wanted to do. We wish he lived 12, 20, 30, but really high quality, 4 years, and a wonderful gentleman. So the other thing we learned is that this is a fairly well-tolerated regimen, giving this relative to, say, chemotherapy. So here's a big hope, which is very important. Can we do this less toxicity for the patients? We're still searching so we can identify these individuals in ways that I'll end with in a moment. The second thing that happened is from that trial of epigenetic therapy, some patients didn't get better or they progressed. So this patient finished the epigenetic trial but still had all of this white stuff here, which shouldn't be here, on the surface of his lung. And he happened to go into the next set of trials, which were among the first trials for what you hear about on television and which is so popular today and has changed cancer in great ways, immunotherapy. So he went on those immunotherapy trials. There were 5 such patients. 2 of them went longer than you would expect them to do otherwise. But these 3 patients, this is a dot that shows their tumor mass, 3 patients. Tremendous drop, stayed down. These 2 patients were alive 6 years out. This patient unfortunately died, but the tumor didn't come back, and that was a result. Immunotherapy can have toxicities. And my wife's probably calling me. I'm going to have to cut her off. Okay, we'll let her ring. And so we've started trials to try and see if we can repeat this and determine whether it's the epigenetic therapy that's helping and to cause this. We have to manipulate simple things in these trials. We started off giving a short epigenetic therapy and then coming in later with the immune therapy, which I'm going to explain to you. And then we moved the immune therapy up front more and extended the epigenetic therapy with early promising results that this may help. Early, but it's indicative of what we do and how we manipulate things in the trials to get things done. What is immunotherapy? Well, it can be explained, it's complicated, but it can be explained in a simple way, the immunotherapy that we're using. So this is a so-called immune cell, a T cell. And this T cell has the potential when it interacts with a tumor cell to kill it. But there's a problem. when this happens long term, the T cell is seeing the tumor cell. The tumor cell actually, through a protein it puts on the surface right here to interact with another protein coming with the T cell, can say, stop working, T cell. You're exhausted. And it can actually do this, and this was a fundamental finding. So what the immunotherapy does, it takes either an antibody to the surface protein on the T cell or the surface protein on the tumor cell, and it breaks that interaction. And now you have the potential, if you can bring that tumor cell in, break the interaction, that you've got a working attack by that immune cell on the tumor cell. This is the immunotherapy that many of you may have heard so much about. So why should the epigenetic therapy help it? Okay, and I'm going to take a complicated slide and make it a bit simple. So we discovered in Peter Jones's lab, work started in our group at Hopkins, published together in a journal that had this cover on it, which is a monarch butterfly. And it's because of the way the drug worked to make the tumor cell think that it had activated viruses within it. And it was called viral mimicry. So the monarch butterfly has this head of a lizard on it with an eye here, and it has an owl with an owl eye here, making the prey think it's already being attacked. It's mimicking, and so they chose to use this on the cover. But what it does is it wakes up viruses by unpackaging them that are normally silent and are part of our genes. We have a lot of viral genes that have been silenced and are with us. When the cell sees that, it says, okay, I sense those, and it goes through a bunch of steps you don't really need to understand for this purpose, but at the end of the day, it causes that tumor cell to respond to the fact that it thinks it sees a virus by sending out an attraction signal that can bring in those immune cells. And we think this is a fundamental underpinning of what our drugs are doing. It's causing the tumor to talk to the T cells better. And this is what we're testing when we go through these trials. Now, we do something else. This looks complicated, which is a fundamental part of what we do. We take that fundamental science that I just explained to you, and we track it during the patient's course. These patients are very brave for this trial, for instance. They will come in and we get a biopsy before you start therapy, and then we get a biopsy early in the trial, 2 months after the therapy. And we go to work and map all these genes that we think are participating in a way that I think I can explain to you here. So these genes are what we sequence them, but what's important here, this is a cloud of all those genes. And after the therapy, compared to if the direction of the genes goes this way for these dots, each of the dots is a gene, then it means the gene went up and got potentially unpackaged with the drug therapy. And they're key genes that we might want to go down that would fight against this. So this is a short-term, these are 3 patients that survived 14 months or less on this. They got some dots in the up range and down. But look at these 3 patients who survived from 21 months out to several years now. They're reacting to the drug by many more genes going up. And among these genes that go up are those viral genes that I just talked to you about, the genes in that sensing pattern. They're all coming from this range here, and key genes go down that would otherwise fight against this. And we can map this. And then the final thing that we're trying to do is make this visual in tumors so we can biopsy the patient and quickly look at a slide and tell what's happening. This work is going on here at the Van Andel. Galen Hotstetter, a pathologist with a graduate student now at Hopkins, have worked together to try to develop this. It's now just coming into monitoring our trials, but here's what we're trying to do. So this is an actual patient's lung cancer, I think. And the black dots in this panel are those T cells. And they're in here, but look at this. This is the tumor. This is the tumor. And the T cells are not inside the tumor. They're hanging around on the outside. So we would think we need to do what I just told you, use the drug and see if we can get them to come in. And we measure some of these viral pathway proteins and say, okay, several of these are low or not where they should be. They're not in the tumor and they're around. And that correlates with the T cells not being where they should be. Contrast this, and we're getting early evidence that the drugs can do this. Now, this marker for the viral pathway is high. This one's high. This one's exactly where it ought to be, right on the surface of the tumor cells, and this tumor's packed with those T cells. And we can visualize that. And the hope is by biopsying each patient, and we can develop a more clinically, we want the sequence, we can really use this more in real time to do this. So I'll finish by hoping that I've given you a snapshot of what Trina gauged, what that fireman gauged, and how this unique arrangement that the Van Andel Institute and Peter Jones and others crafted to reach out in the way that I told you around this wheel with this collaborative power. Let me show you another success that a team like ours is proud of. You can't read this, and you can't read this because each one of these things going down the list right here is a clinical trial ongoing in this country at another place or around the world. But they're all trying to do the concept that I just told you in one way or another, using drugs like we're using to try to stimulate the immune activity and recruitment of the cells. And that's a success where the Van Andels reached out even further, because maybe it's in their trials taking this concept. Maybe it's going to come from some of ours, maybe it's going to come from some of theirs, but the goal is to make it happen. So we're not there yet, but the promise is, and I've tried to show you how we try to exploit that promise to learn, and it's the promise that keeps the dream in our team. This is what we'd like to see happen. So thank you. It's an honor to get to talk to you, and I hope I've clarified this mission a little bit. Thank you very much.
We'll have an opportunity to listen from Dr. Steensma following, again, a second brief video. And then following Dr. Steensma's presentation, we'll have time for questions and answers as well.
I really don't consider my work to be a job. It's really a personal mission. Every day has its own unique potential, and I spend my time exploring it. Nathaniel is a young man who I saw first as a patient who had a horrible disease. It's called an aneurysmal bone cyst, and this tumor was in his spine and was causing significant pain and nerve damage.
When I first heard about the tumors, it was heart-wrenching.
Nathaniel was a very active, healthy, wonderful kid, but this tumor had really impacted his life. We found a target in his tumor that matched a drug that was typically used for osteoporosis, not even cancer. And with Nathaniel's guardian, his Aunt Darlene's permission, we gave him that medicine, and he had a very dramatic response.
With everything that Nathaniel has went through, he still kept a good spirit about everything. And that makes me look up to him.
I look around me, and there's incredible technology and bright minds and people who really care about patients. My job is to take all of those and put them together to help people like Nathaniel.
Whatever I need to do or whatever sacrifices I need to take for him to be better, I'll take it without a blink.
Nathaniel's treatment is not over. Because of the rareness of his disease and the uniqueness of his response to this drug, more research needs to be done. Rare pediatric diseases are understudied. It is very hard to fund research for rare disease in general. Donor support, philanthropic support, is essential to studying rare pediatric diseases. Being able to do this type of work, to see research improve human health in real time, it's the most rewarding job in the world.
Stories like Dr. Steensma and Nathaniel are powerful examples of hope in a seemingly hopeless situation, and are just one of hundreds of inspiring stories that are happening here at Van Andel Institute. They are tangible proof that the discoveries that happen here touch lives. Stories that would not be possible without a dedicated team of scientists and researchers, and more importantly, stories that wouldn't be written without our gracious and generous community. Your belief and your support is truly changing the course of history. making miracles happen, and making such a beautiful difference.
Please welcome Dr. Matt Steensma.
Thanks, Brett. When you see yourself on a video, it's kind of surreal because he looked so young, didn't he? He was so young. And then I'm like, oh no, that was only 3 years ago. It's interesting. I sort of live in two worlds. I live in the medicine world and I live in the scientific world. And they really are different cultures, different environments. We communicate differently. The personalities are different. But one thing where there's a real common thread is that on both sides of the street here, there are an equal number of incredibly passionate people about caring for patients. And we sort of view science as this objective, kind of cold, professional environment where we analyze data and look at things in black and white, but it's really not. As in my role, it's really gone past the point of being a manager or a leader. I get to basically be the head of a team of people who are incredibly excited and motivated because they have loved ones with the diseases that we're studying. So my role is really a headship role, as opposed to some of these classically defined business terms. And I hope you get that out of my presentation. I wanted to tell stories today. I think oftentimes that's the best way to understand science. But I also want you guys to really begin to see the heart of the people doing this work. And I thought the video captured the essential sort of frustration and some of the pathways to innovation that we follow. And in full disclosure, my lab, we do a number of things in our laboratory. Our primary disease focus really is not bone and bone tumors so much, but a lot of what I'm going to talk about here is bone tumor because that's where we've seen some of the biggest results in improving patient care. But we spend a lot of time and energy studying diseases that have mutations in genes in the RAS signaling pathway. RAS is a very well-known pathway in cancer, but it also affects human disease in many other ways. So we study a rare genetic disorder called neurofibromatosis type 1. And then we also study the most prevalent cancer in the world, which is breast cancer, because a lot of breast cancers also have mutations in the NF1 gene. So a lot of our work is focused on that from a disease standpoint. But when a patient sits in front of me and the playbook is narrow, if not absent, my first gut instinct is to take the problem to the laboratory. And what you saw in the video there was good evidence of that. This is Nathaniel's MRI before treatment. And just to orient you here, this is Nathaniel's spine. This is his bladder. You can see that bladder is really big. He can't pee because he has compression of the spinal elements. And this tumor here, which looks like vertical blinds, this is all the tumor. It's completely destroyed his sacrum. It's growing out the back of his spine. He had almost about a cantaloupe-sized mass coming out of his backside. And every area, every little kind of loculation and cavity in this tumor is filled with high-pressure arterial blood flow. This is an inoperable spinal tumor. And he couldn't walk when he came in. He had pain beyond which we could manage with pills. He had to be admitted. And there's a whole story about how it got this big. But there is no treatment for this. So when I passed this around to some of my surgical training colleagues at Memorial Sloan Kettering Cancer Center, they kind of shook their heads and said, that's going to be a rough road for that kid. You know, we don't have options. And there really is not much innovation occurring in this type of tumor because it technically is a benign tumor, even though it can kill people if it's in the wrong place. So Deanna Mitchell, who's one of my favorite physicians, one of the most respected physicians in this community, I came to her with a question about how to treat this, and she and I hit the books. We had this child lying in bed in the hospital, hard to control his pain, and we spent a lot of time reading and trying to understand better how this tumor functions. And Deanna's a pediatric oncologist, so she went through all the chemotherapy regimens. I went through some of my bone medicine regimens, and we actually had some of these tumors banked in my laboratory. So what I ended up doing was working with a couple people in my lab to try to test these tumors to see if we could find a target. This is 10 weeks after treatment with a medicine called denosumab. It's a mouthful, but basically it's a medicine that targets one protein only. And this protein is incredibly important for bone health. It was originally designed for osteoporosis. That medicine targets a protein called rankle. There's a long term for this acronym that I won't get into. But based on our research, we decided we would try this medicine because aneurysmal bone cyst, this tumor expressed a very high level of this. So this whole strategy sort of began 7 or 8 years prior when I was in my training. I trained under a gentleman called his name is Stephen Goldring. Dr. Goldring gets credit for discovering calcitonin and the calcitonin receptor, a very powerful bone mineral metabolism protein. He successfully cloned that receptor, and he was the head of research at a place called Hospital for Special Surgery, which is the #1 orthopedic hospital in the world, arguably. So Dr. Goldring oversaw the entire portfolio of research at this hospital, but I got to spend a year in his lab. And so he challenged me to start looking at bone-eating tumors. And so what I would do is my job was to get the tumor out of this operating room, and then I'd separate the cells and I'd grow them in a tissue culture dish. And then I'd have to add different reagents into these cells and see what happens. Well, we were really focused on these sophisticated technologies. We had polymerase chain reaction, we had protein analyzing machines, and all these things that are big and powerful and expensive. But one day, I got this result where I put 3 different products on these cells, and one of these things doesn't look like the other, just like Sesame Street, right? And so I brought this culture dish to Dr. Goldring, and he got very excited, and I had no idea what was going on. But Dr. Goldring said, you know what, you've changed the morphology, you've changed the shape of these cells, and this is a very important observation. Well, we didn't understand this by the time I left. We never really had a chance to look into it, but it was such a dramatic effect, the experience stuck out of my mind. And when we started looking at aneurysmal bone cyst, which is what Nathaniel had, the tumor, I began to think back to this experiment. And what we saw, these big cells here under the microscope, they're kind of purple, and they have lots of little purple dots inside of them. Those are bone-eating cells. And if you compare under the microscope how aneurysmal bone cysts look, you see these same big bone-eating cells in just open areas. And so it was reminiscent of the aneurysmal bone cyst. And what we found out within a few years after me leaving Dr. Goldring's lab is that some of these cells, which are giant cell tumor cells, have a really high expression of the rank ligand. And that's where we got the idea to look for rank ligand in the aneurysmal bone cyst. Fast forward, maybe I would say a month after we had Nathaniel in the hospital, the person who made this discovery in my lab, his name is Pelle. He's an orthopedic resident. And for those of you who don't kind of understand orthopedic surgery, orthopedic surgeons are usually at the top of their class when they graduate med school, but all they do is focus on bones, so by the time they're done with residency, they're at the bottom of the class. And so it's this joke that orthopedic surgeons sort of lose their kind of intellectual curiosity, and they lose a lot of their sophistication in medicine. But Dr. Pelle was an outlier. He didn't want to just do joint replacements his entire career. He wanted to be a spine surgeon. He had a very intense interest in science. So despite his wife's advice, he decided to get another scientific degree during his 5 years of residency program. So he was in my lab trying to answer questions, and he actually took care of Nathaniel. He was part of the process, and he was really, really compelled for this child. So he was up until 2 in the morning running this experiment, and of course he calls me at 3 a.m. to let me know the results because he was so excited. But what he found, he was the first to show that this tumor has a high level of expression of the rank ligand, which is our drug target, compared to what we already know expresses the rank ligand. And then he did some fluorescent studies to show where it was in the cell. That's all this green stuff. And so his work really laid the foundation for using this. We now had a scientific rationale to try the drug in the child, and then we got the Aunt Darlene's permission to do it. And the rest is sort of documented here. Nathaniel is now over 5 years from treatment. We think he's cured of his disease. He's been off denosumab for 3.5 years. The tumor has not recurred, and he's back to school. He's not perfect. I don't want you to get the impression that everything's rosy, but compared to the options which we had in front of us, he's drastically better. So I tell this story to really highlight the two-way street that happens here. There's a two-way intellectual street, there's a two-way regulatory street, there's a two-way street in terms of compassion for patients. And even though this is just a single case, the power of this case is really impressive. So denosumab has now become standard of care for our aneurysmal bone cyst patients. They usually would get morbid surgery, and now they're getting medicine, a shot once a month. Not all the kids like the shot, but it's much better than a big surgery. So this is an example of where the science and the clinical work has really come together to help a rare disease. There's always the law of unintended consequences when you're working in discovery. And I think Dr. Balin talked about this well in terms of the phases of the clinical trials. We try these new drugs in phase 1 trials. We don't know their side effects until you really ramp up the doses. And even if it works great, if 50% of the people that are cured by this tumor have such bad problems from the drugs, it won't get approved by the FDA. It's too dangerous. So at the time, we were looking for known side effects of denosumab, but we didn't know what we didn't know. So this child received almost 3 years of a drug that inhibits calcium resorption. And so he deposited huge amounts of calcium around his growth plates to the point where on the x-ray, you could see this from across the room. It wasn't slowing his growth down. He didn't have pain. We weren't sure what the consequences were. Well, coming off the drug, about 6 months afterwards, all of this calcium liberated into his bloodstream, and he had a life-threatening high calcium level. And for those of you who know calcium levels, it was a serum level of 19 milligrams per deciliter. Human life usually stops around 15 milligrams per deciliter. But because he was a child and he had the kidneys of a child, he was able to filter this up until a point. He ended up going on dialysis for about 3 weeks, filtered all the calcium off, his kidneys were okay, his bones were okay. But if you think that discovery is all like it looks like in the video, it's not. There's absolute risk in discovery, and there's absolute risk to patients on clinical trials. But if you don't do it, nothing improves. So it really does take a lot of courage on the part of patients going into clinical trials, on the part of physicians to accept the risk of putting patients through these trials. And it's a very, very rewarding process, but you just have to be incredibly good at what you do and have a system that supports clinical trials to do them well and safely. So the whole concept of targeting an essential protein in bone has overlap. And again, this is the ripple effect of Nathaniel's case. So Jess Foley is a pediatric oncologist at Helen DeVos Children's Hospital. She was also in my laboratory at the time Nathaniel received his treatment. And Jess is in practice now, and she has a patient that has a condition called Noonan's syndrome, where every cell in the patient's body has a mutation in one of the RAS genes. In this kid's case, it was PTPN11. And he's about 12 years old, precious age. It's very hard to be different at age 11, 12, 13, right? You just want to be part of the crowd. You don't want to stand out. And he had tumors in his jaw from this Noonan syndrome that were so big, it basically ate his jaw away. And so his cheeks were about 3 or 4 times the size of a normal child. And it was a social issue. He had tooth problems. And one of the biggest problems Mom talked about was he couldn't sleep at night because his airway, this is where the air goes through, it was just so tight from these tumors that the air couldn't pass well. So there's no treatment for this. There's surgical treatment, which is basically debulking, but the tumor grows back quickly, and kids will have dozens of debulkings by the time they're in their 20s. Very morbid treatment, very brutal on the child. So Dr. Foley recognized this type of tumor as having big cells in it, kind of like the aneurysmal bone cyst. And so she called around, and she felt like she had sufficient scientific rationale to do an experimental therapy on the child. So she gave the patient denosumab, and what we saw was quite profound. So this is the before picture. See all that gray area? The bone is missing there. Compare that to 4 months of denosumab therapy, where not only is the bone smaller, but it's consolidated now. And it was interesting. Mom came in at the 2-month point and said, yeah, he's not snoring anymore. And then at 4 months, he's getting a full night's sleep. So again, we think we've come up with something here, but we also know that there are risks, there are challenges with this drug. So this all looks great, but we don't honestly know the effect it will have on his Noonan syndrome. We don't know the effect it will have on his calcium regulation once the medicine stops. We don't even know how long to treat the child. So there's a burden of care that we have to meet for any given individual that our research doesn't always inform us on how to do it. Another case, so this is a different type of rank ligand inhibitor. We're applying it to a different type of bone issue. It's called a bone cyst or a unicameral bone cyst. This is different than what Nathaniel had. Unicameral means single chamber. These are very common in the pediatric population. They're a big reason why kids break their bones, and they eventually go away in adulthood. They're not cancer. But if you take a 16-year-old volleyball player who's trying to play Division I volleyball, and every time she spikes the ball, she either breaks her arm or it hurts really bad, it's a big deal for her. So there's a burgeoning kind of area of research here, and there are a number of treatment options for these. But when you start talking about them, the effectiveness of them, the risks of them, you realize that the playbook kind of sucks. And so a lot of families that come in, they're really looking for a fix, and there's just nothing good. There's nothing within 3 or 4 months that will make their child better. And so it's a labor of love to treat these, and the fracture rate is really high, so they keep breaking, and so it creates problems. This novel rank ligand inhibitor is not a shot. It's like under the skin. It's not a pill. You actually inject it right into the cyst. And so we're on our third patient now, and what we're finding is within 2 months, the bone cysts are filling up quickly. And so far, the side effect profile of this medication is very good. So, imagine these are all novel treatments. These are all new ways of treating different problems, but they originated from one patient. And that's often the value of treating rare diseases, is that you learn something about the disease or the pathway of the gene that then applies to something broad. I want to change gears a little bit. Dr. Pelle did a beautiful job of explaining DNA and explaining how DNA is the hardware of the cell, and the cell really runs the software package. Roughly early 90s, there was a huge push to sequence the human genome, to basically publish the DNA sequence of an entire human's cell, and from that develop technology to work with DNA. And as you probably know well, just even reading Time Magazine or New York Times, DNA is an underlying cause of many diseases, not just cancer. In fact, even though we can sequence DNA really well today, we still don't understand it all. Some of the most powerful genes in the body, when they're mutated, they create a syndrome, a genetic syndrome. So patients have mutations in lots of parts of their body. Those mutations make the cell dysfunctional. And if the cell's dysfunctional, the tissue, like an organ, is dysfunctional. And so many mutations don't have, or many diseases don't have recognized mutations. Nobody's really gone through the work to discover them. And for the diseases that do have known mutations, there have been a lot of treatment advances. So there's this really important sweet spot in finding mutations that cause human disease. And in West Michigan, there are a lot of patients, a lot of families like this. This was really Bart Williams' brainchild. I don't know if Bart is here, but this is something within a year of starting at the Van Andel Institute, Bart recognized that I was seeing patients with a lot of rare diseases. And so he said, well, why can't we sequence these diseases? Why can't we find the mutations and try to help patients that way? So we developed something called the Outliers Program. And one of the first patients that came to mind, literally weeks after Bart had this idea, was a patient that had a condition called ocular ectodermal dysplasia. It's a mouthful. OED or OES is the good abbreviation. Oculo means eye, ectodermal means skin. It literally means disorder of the eye and skin. And the person that discovered this syndrome is Helga Torriello. And Helga was a practicing geneticist here back in the early 90s. And there were 2 patients here actually that were basically identified in the NICU, the Neonatal Intensive Care Unit, as having problems with their skin. They're born with patches of skin missing. And then they also have little tumors, benign tumors on their eyes. But those 2 features were very characteristic of this syndrome. So Helga went through the work of describing the syndrome and comparing and contrasting it to every other syndrome that might be similar. Fast forward almost 25 years, one of my high school classmates, her daughter was born with ocular ectodermal dysplasia. And ocular ectodermal dysplasia is one of the more rare syndromes you can find. At the time, I think she was the 16th patient ever reported as having this. So you can imagine if there's 280,000 women a year diagnosed with breast cancer, the playbook for breast cancer is going to be massive, right? There's a ton of patients that have it. There's a lot of federal funding for this disease. Compare that to somewhere, over 100 years, only 16 patients have it. There's an empty playbook. There's nothing you can really do about this short of discovery level research. So Addie has allowed us to use her pictures, and Rachel and Addie gave an interview. And if you're interested in Rachel's perspective, it's on the Spectrum Health Beat story. It's a very interesting article on her condition and the trials she goes through. The way that we discovered her mutation was basically through a bone lesion. So Addie had spots on her bones that were benign bone tumors, but they were behaving much more aggressive than usual. These are called non-ossifying fibromas, or NOFs. And some of these tumors were getting so big that her bones were starting to break. So she needed surgery to remove the tumors and fix the bones. And at the time, we were able to take some of that tumor tissue, take some blood, and sequence all of the DNA in her body and look for mutant genes. And what we found was in these tumors, there was a mutation in a gene called KRAS. KRAS is probably one of the more potent oncogenes or cancer-causing genes we know of. If you look at the potency of different mutations in different genes, KRAS is right at the top of the list. But Addie doesn't have cancer. So this finding was profound in many ways, but the fact that the mutation, the G13D mutation, was sitting in a site in KRAS that does a lot of the business end of the work, it told us not only would these mutations make her disease worse, we were probably going to learn about the function of this gene just watching Addie grow up, because these mutations were not just in the bones, they were in her muscle, they were in her skin. This chart has a little kind of blip on her bone marrow. It's in her lung tissue. And what's interesting is it was not there at a 50-50 ratio. So all of our genes, you have one copy from mom, one copy from dad. So if you have a mutation that comes from your mom, you would expect 50% of your genes in any tissue to have the mutation. Hers were not. Hers were in kind of a random order. And what that is, it's called mosaicism. So what that means, it probably was not a condition inherited from her mother and father. It probably arose when she was developing very early in the womb. And so only a proportion of her body received the mutations, and the tissues were mixed. So here's a microscopic picture of her muscle. This red area is a tracer for a protein called ERK, and ERK is a marker of how high the RAS pathway is activated. And what you can see is that there are muscle cells that really have no ERK activation. They seem very quiet in terms of ERK. And then you have these other cells that are quite bright. That's the mosaic pattern. We presume that this cell had a mutation, that's why ERK is active. This one did not. And the same is true of some of the cells that express a protein called STAT3, these little cells on the side. These are probably immune cells. And so the mosaic pattern is something that honestly doesn't make it any easier to treat, because if it were in every cell in the body, you might be able to get a better global picture of how to treat her. But if it's just one tissue or another, you really have to develop an independent strategy for each of these tissues and organs. So not knowing where to go next, a very, very bright research technician in my lab, Patrick Dischinger, he's very good at working with rodent models, mice, rats. He developed this beautiful rat model of breast cancer, so he inherited the nickname Ratrick. Ratrick decided he was going to try to create an avatar mouse model of Addie. And we knew her mutation. There wasn't an existing mouse model with this specific mutation, and there wasn't a way to kind of express it in the tissues we wanted. So Patrick went through the process of developing a mouse using a technology called CRISPR-Cas. Raise your hand if you've heard of CRISPR-Cas. So CRISPR-Cas technology has hit the lay press because of its power. It's a very interesting read. So to put in perspective, even 15 years ago, it would cost millions of dollars and sometimes take even a few years to cut out one gene from human DNA. It could be done. You could do it a lot easier in mice than humans. There was a group that discovered some enzymes from bacteria, and if you put them in the cell in the proper way, this mouse took about $4,000, and it took 2.5 months to make. So if you consider any technology as it evolves in any industry, if over the course of a year you go from millions of dollars in years to produce something to thousands of dollars in months, you can imagine the impact that has on any economy or any business. Well, science runs very much like that. And so CRISPR-Cas is probably one of the most powerful scientific discoveries, certainly in my lifetime, but this may end up being something very, very important. So I encourage you guys, if you haven't heard of this, give it a read. It's both incredibly exciting and incredibly scary. A lot of people have compared it to nuclear technology in terms of its potential to both help and harm. When we use it in the germline of mice, what we do is basically inject these enzymes into a developing mouse embryo. And what comes out is basically a gene that we cut a piece of DNA out and reinserted the mutant sequence. And so Patrick spent a lot of time designing the actual enzymes and all the DNA sequences. And on the first try, about 25% of all the embryos actually had the correct sequence. So it was a big win. And so this mouse was the recent kind of study subject for an investigation comparing different types of KRAS mutations. Colon cancer has different mutations than pancreatic cancer, than lung cancer. And all these mutations, we strongly think they're going to be biomarkers. I mean, if you have mutation A in your cancer, you're probably going to respond to drug A. So there's a lot of information that's needed. We need to determine how this mutation responds to drugs and affects development compared to other mutations like G12D, which is just a neighboring mutation. So this is a group from Harvard. Kevin Haggis and his lab took our mouse and began studying the potency of these mutations. And Addie's mutation is right in the middle here. And so this basically tells you how potent the gene is in its mutated state. And hers is kind of in the middle here between normal and then the super potent G12D mutation. And when they put it in the mouse, they looked at the colon structure because G13D is often in colon cancer. And what they found is that it absolutely affected the development of the colon, but it didn't destroy the organ. So what you have in Addie's case is a mutation that literally sits in the middle between normal tissue and organ function and really what is incredibly damaging mutation effects that cause death of cells and drastic dysfunction and cancer predisposition. So, you know, if you ever wonder what God's grace looks like on a graph, that's what it is right there, right in the middle. And the findings in this study have been well received, and what it tells us is that we probably have to target these mutations differently. We probably need a different drug strategy treating a non-cancerous condition with these mutations than a colon cancer or pancreatic cancer with these conditions. So the translational cycle goes from very, very basic research that was inspired by a patient. The longest climb is getting from basic through the clinical trials so that you have an FDA-approved medication that can help many, many, many people. And so, you know, again, Stephen put Van Andel Institute's role in that beautiful slide exactly where it sits. And David Van Andel likes to talk about disruptors. He likes to talk about people who aren't following the normal course of investigation so that we can speed things up a little. And I think when you start really looking at the power of having patients involved in research in terms of tissue donation and then having basic science results going back through clinical trials, this is really where that all happens. And you definitely need someone to catalyze these things. They don't happen naturally. In fact, sometimes you have to really leverage and push to get anything done. So having an entire institution to support that, it really positions all of our work in a way that allows us to help people. This is the current list of, actually there's 34 now, of candidates that we're looking for mutations in or considering including in the Outliers program. And this is a pretty old list, actually. Chances are in the next 10 years, any disease is going to be sequenced that we're going to find out the mutations for the disease. That's certainly true of the common conditions like diabetes and some of these other problems that are more everyday problems, not cancerous problems, but still horrible problems. If you want your disease on here, let me know. So many thanks to a whole team of people that perform this work. And science is a team game. And teams have to perform at an extremely high level. and teams have to share a mission to be successful. And so everybody on this list is really handpicked because of their expertise, because of their passion for helping people. And what you'll see here, and this is in my lab, there's a diversity of people. There are physicians in training, there are graduate students. We had Patrick started out as, he got a master's degree and started out as an assistant technician. And now, because of his contributions, he decided he wants to be a principal investigator. So he's in the graduate school at the Van Andel Institute. And what you find in science is you begin to develop generations of scientists that really, really are passionate for this type of work. And so I'm just deeply grateful for everybody who's supported our work, and it's a long list. This is just a few here. Thank you for your time.
Well, if no questions, Dr. Balin and Dr. Steensma will be up here following for just a few brief moments. Thank you again for taking your time. I hope you got a glimpse of the complexity of what it means to take basic science into the clinic and then back from the clinic and back into basic science, and that you also gained an understanding of the depth, breadth, and complexity of an organization like Van Andel Institute with the global collaborations that we have. We're grateful at the Institute for the generous gift that Jay and Betty made to launch the Institute. We're grateful for the work that individuals like Dr. Balin and Dr. Steensma can do. And we're grateful for folks like you in this room. Dr. Jones often puts it, we can't do this work without a home team advantage, and we consider Grand Rapids our home team advantage. So thankful to you for being ambassadors for the mission, for the cause, for the work that we do to impact human health so that we can cure these diseases that occur in pediatrics all the way through our lifetime, but that we can impact global human health. So thank you so much for joining on the journey. You're welcome to join us or befriend us on Facebook. We have a lot of information on our website. You can join the Purple community. Again, we cannot do the work without an entire community of people that surround us. So thank you for joining us, and join us again in the future.